do some introduction about it, and then do some show and tell about an algorithm we built. And yeah, but first I'd like to give the word to Willem.
Okay. Yeah, thanks. Thanks to our every other 6 weeks or so, we do a pizza session like this. Last time was not everything is a data frame, and we have many of those. It's great to see some people that are back. As you know, we do this as an internal thing within PA Consulting, but we also decided that data science isn't really just ours. It is a wild and wieldy platform or group of people out there that just like doing tinkering with software and doing data science-y work. Why not share our insights with other people in a good tradition of open sourcing what we find. I think there's no one that would deny that the reason that data is so sexy today has a strong bearing in the fact that some time ago people decided to open source their ideas. And this is built on giants that have open sourced their finds. So in that tradition, we decided to open this up a while ago already. And obviously, we're a commercial company, we're PA Consulting, yada, yada, yada. But we still like to open this up. And I think this is the first time where the number of non-PA people actually that have signed up supersedes the number of PA people that have signed up. So that's great, and I really like that to progress. Next one will be in January. At the end of the session, we'll talk a little bit about that. First, of course, we are a commercial organization. I would like to hand over quickly to Anna, so she can talk to us about how great PA is.
Thank you, Willem. I'm going to do that really awkward thing where I try and share my content and you realize I'm not a data scientist and I'm a massive fraud. So give me 1 second. I'm just going to, and I'm going to use can everyone see my screen? It's our favorite phrase at the moment.
Yes, we can.
Okay.
Now I kind of feel a bit awkward that I left the pizza and the Python pictures on, but we'll go with it anyway for future events. So as Willem said, I look after our data analytics recruitment in the UK, and obviously we are absolutely actively hiring across our different European offices. So Utrecht, we also have a really exciting growing team in Denmark and also within the US. So I am going to try and get you interested in looking at our careers page after this. And obviously any questions, link up with me on LinkedIn. But just really briefly, I mean, we are the oldest consultancy in the UK. We are, as we said, we're a mixture of strategists, designers, digital data scientists, and we work globally, so across the UK, US, Europe, and the Nordics. And some people don't know half of the really cool stuff that we've done. We have a laboratory in Cambridge where we've had a history of sort of developing brand new products. So some of the stuff that we're involved in might be around customizable makeup. We helped to develop the edible water pods, which you may well have seen being used at quite a lot of the marathons this year. We are helping to drive the sustainability challenge with developing new types of biodegradable plastic. And in case some of you like a beer, we actually invented the widget quite a few years ago. So I think we're resting on our laurels a little bit with that one. And just to give you a bit of a broader overview, in case you're thinking, what kind of roles or what kind of, consulting could I get involved with at PA? We really are an end-to-end innovation consulting firm. So obviously we're talking about kind of analytics today, but we also have a digital offering, architecture, agile, and obviously data science and into our digital trust space as well. So if there are any roles or I suppose at any level, we've just opened our grad scheme as well, then please do have a look and I'll show you in a second the kind of roles that we're looking to hire. Oh, there we go. And I think what's brilliant about PA is, the session that we've got today, both for external and internal people, is really the kind of offering that we want to do outside the work hours as well. So some of the ladies on the call and some of the guys will be heavily involved in our Code First Girls relationship. A lot of the guys on this call will also be going through their cloud certifications, and we have a lot of very strong networks, including our BAME and our Pride network as well. So people come to PA to do really interesting work, but also to really sort of bolster their own qualifications and enjoyment as well. And before I let you get on with all the coding, just to give you here's my dramatic graphics in the top right corner, is just to kind of give you an idea of kind of how broad and the roles are that we're recruiting for. Please do not ask me what half of these are in the digital space. But as I said, if you are at all interested in roles with us in any of our geographical locations, do add me on LinkedIn, have a look at our careers website. But it's a really fantastic time to join some really cool projects and really interesting new clients we're working with. And that's it. I think I bored you enough.
Right. Thanks, Anna. And I've been with PA for 21 years now, so I can say that there's there's not a lie in your words. Right. So yeah, we had to do the lookie, of course. Thanks for that. I would like to hand over to Ismail, who's going to walk us through genetic algorithms.
Yes.
Ismail will do the theory, and then Suzanne will talk us through some example code that we've created for this.
Yes, thank you very much, Willem. I'm going to share my screen. I hope that I have a stable internet connection, so if it reduces, please do tell, so we can take measures accordingly. All right. Is everyone able to see my screen?
Well, I can't talk for everyone, but I can.
Yes. All right. So thank you very much for joining, everyone. Today's pizza session will be about genetic algorithms. So I don't know how much of you guys people are familiar with genetic algorithms. How many you has hands-on experience of genetic algorithms? If so, could you please raise your hand so I can get a good feeling of what you know, and to get a feeling myself of how many people even have familiar experiences with it. And it's immediately climbing above 9+, 10+ actually, so that's over a third of this group, which is really cool to hear. So for those that don't have a lot of experience on genetic algorithms or don't really know what that exactly is about, genetic algorithms is all about trying to find a solution to a optimization problem, like for example in machine learning. So machine learning is all about learning how to do predictions in case of supervised machine learning, of course. So what you do is you have a model in place that tries to do really good predictions based on your input data and the weights of the model itself, and then comes with prediction. It uses that prediction then to minimize your loss function. So and that is where optimization comes into play in machine learning. So changing the weights as such that your loss function is minimum. So how do you know when your loss function is minimum? You have a lot of techniques that you can use, like optimization techniques that figure out how to minimize, to find the right set of weights that minimizes your loss function. So, but this is very specific to machine learning. Of course, you can apply optimization techniques to a lot more problems than only machine learning. Like we will give a show and tell on a piece of code. I don't want to spoil what it is about, but we will use optimization techniques for a solution that doesn't have anything to do with machine learning per se, but it is much more than that. So when we so we can generalize the optimization problem as this one, what you see at the left side over here. So we have optimization, objective functions, and objective function is the function, like in this case, the loss function that we try to minimize or maximize. That is our objective function. That objective function is subject to some constraints. We have J equality constraints and K inequality constraints, where X then is our input factor. So this is the most general form of optimization problem that you can define. And then it is all about applying an optimization the solution to it. So to give an example, because yeah, this is general, so it can be a bit confusing, to give a rather simple example to get you familiarized with it. So let's say we have a function that looks like this, and we want to minimize that function. Now, this function can be subject to this inequality constraint and these two equality constraints, like the x values has to be positive, and the minimum has to be 0. So if we apply this constraint to this objective function, we will find a solution that says the minimum function is 1 at value 0. But this is the most simple form of an optimization problem and its solution. So of course, obviously, we as data scientists deal with much more complex situations than this, where we have to try to find a solution to an optimization problem, and that problem can be very diverse. You can have an optimization problem where you do have constraints. You have optimization problems where you don't have a constraint, and then yeah, you have problems where you have types of constraints. Then you have types of objective functions. You can have objective functions that don't have an analytical solution to it, or don't have gradients at certain points to it. You name it. Lots of different types of optimization problems that you can have, and you want to find a technique that has to be diverse enough so that it can deal with all these types of problems. So when it comes to techniques, optimization techniques, in terms of classifying its behavior, there are 3 classes or 3 categories of algorithms that you can use, that each behave a bit differently to a certain problem. So like one class of techniques are what is called deterministic techniques. I don't know whether you're familiar with each of these two, but you have like linear programming, nonlinear programming, gradient-based methods like the Newton methods or the gradient-free methods. These techniques are all deterministic techniques. They are deterministic in the sense that every time that you apply that optimization problem, behaves exactly the same as it behaved before. So it doesn't change its behavior. It's very operational and exactly this. And then you have stochastic algorithms. Then that can be classified into 2 parts. We have heuristic optimization techniques and meta-heuristic optimization techniques. These optimization techniques are not deterministic, as the name implies. It's stochastic. It means that it works with some sense or to some extent of randomness. And then you have a stochastic learning that uses deep learning with stochasticity to it. So why am I telling you people this? Is because based on the type of optimization technique you use, the way how you will solve the solution will change massively. Of course, we want to work with the models that cover, with techniques that cover a large space of solutions, and also during optimization finds new spaces every time you run it. So that makes your search a bit more global. And because most techniques most problems that we deal with, we want to perform a global search, we apply stochastic algorithms to it. So you can say fairly that deterministic algorithms are local search methods and stochastic algorithms are global search methods, purely because of the randomness. And I will get into that in the subsequent slides. So how do we, yes, okay. So yeah, stochasticity and algorithm. So why do we want to work with optimization techniques that are stochastic and not deterministic? The flaw of deterministic algorithms, as I just mentioned, is they are exactly repeatable. So if you have an initial starting position and you apply optimization to it, it will always find the same solution. And in classical optimization, that is, they are deterministic in the sense that solution can uniquely be determined by an iterative procedure. The only randomness in global methods is the starting point, which is either an educated guess or initialized randomly. So if you change your initial conditions, yes, the model may change its solution, but that's like the only kind of randomness that you can get in global methods. There are some very, very small exceptions to this, like the stochastic gradient method, which is a deterministic algorithm that does apply a little bit of stochasticity, but it's not much more than that. But I won't get into that now. So for a lot of analytical methods and search algorithms, randomness is avoided. But as I just said, we want to work when we have to deal with the solution. Most of the time, we have to solve solutions where we want to do a bit more a global search. So that is also why in modern trends, you will see that most optimization techniques or problems, they tend to use evolution algorithms and nature-inspired meta-heuristic algorithms to solve such problems. Yeah, in reality, randomness is everywhere. So yeah, there is no strong reason for not using randomness in developing algorithms, and that is why we will talk about genetic algorithms, which is one form of a stochastic algorithm. So, well, genetic algorithms, where does it fall? So when you look at stochastic algorithms, they are always nature-inspired algorithms, because nature is the best solver of problems. It has challenged many phases, and it has always found really good solutions to those. So we as scientists, what we do is we just try to mimic that behavior of nature, so we can make benefit of its knowledge. And that is why we call them nature-inspired algorithms. When you look at such algorithms, they can fall into two groups, which is evolutionary computation and swarm intelligence. Each of these is very interesting on themselves. I can talk hours for hours straight on each of these techniques and the differences between those, but that is not in the scope of this now. But if you're interested, do let me know, so I can also give you really good reading material on each of these. Genetic algorithms falls within evolutionary computation. To give a bit explanation between the difference of these two, or even the category nature-inspired algorithms. So modern stochastic search methods are often evolutionary algorithms. These algorithms form part of what we call evolutionary computation. So loosely speaking, it's a part of computational intelligence in the wide context of computer science and AI. Although when you look into reading materials, the definition boundary can be a bit blurry between these two disciplines, and sometimes it can be a bit more arbitrary, but that's not important. So, well, what these algorithms do is it's all about finding a balance between randomness and regularity. A balanced use of randomness with proper combination with certain deterministic components is in fact the essence of what makes these algorithms so powerful and effective. It is all about finding the balance in these two, because if the randomness in the algorithm is too high, the solutions generated by these algorithms do not converge easily, because they can jump around in the search space all over. If there's no randomness at all, they suffer from the same disadvantage of the standard deterministic models. And each of these techniques works a bit differently in trying to find the balance between randomness and regularity. So finally, genetic algorithms. So what is it about? Genetic algorithms is an evolutionary algorithm, and it is, I can say, probably the most widely used one. It's becoming a conventional and classical method. It does have some. It has like fundamental operators that have inspired many later algorithms, and because of its power and the fact that it has inspired so many later algorithms, we will introduce specifically this one in great detail. It has been developed around the 1960s, so it's almost 60 years back. It's a model or an abstraction of biological evolution based on Charles Darwin's theory on natural selection, and it will be clear in a second as to why. It's the first model that uses concepts like crossover and recombination, mutation, and selection, which are each a very biological concepts. So how it works then? So it starts with, so there is a population, which is you start with a random population of solutions, or solutions, quote unquote, like vectors, input vectors, which is a solution to the model. It's not per se the best solution, but it's a vector that you can use for the objective function. So it randomly initiates a set of these what we call agents, and it calculates for each of those agents, it calculates its fitness. So how good is that agent? And you calculate the fitness of each of the agents, and you apply some form of selection to it. most of the time, obviously, the type of selection you use to it is based on the largest to the least largest one. So you just pick the X best, X highest, the X agents with the highest fitness. But it's not always selecting the best one. It's also good to apply like at least a little bit of randomness to it. So once you have calculated the fitness of a population and have applied some form of selection to it, though that group of agents will become what is called the parents. And those parents, what you're going to do then is you're going to perform a crossover. This is also exactly what happens in cell division, where you have like mitosis and meiosis, but now I'm getting a bit ahead of myself. This is what happens in sexual reproduction. The child takes the genes of the parents, but in different sorts of combination. So what you do is you take the parent genes or the agents and you apply a crossover to it, where you're going to combine, let's say, two agents into either a single agent, or you're going to take half of this parent's gene and combine it with the half of this gene. Do it both way around, so you get two solutions to it. That is then crossover. So you're making children that are a mix of their parents, and then that children you're going to apply a mutation to them, which is very small changes that you apply over here and over there in that vector space of the child. And what you then do is you refill that population with new children to your population set. So what you will have is you have, again, re-emphasize, you have a group of people, you calculate their fitness, you select the best ones, and the best ones you pair them together, they reproduce children, and you're going to do a little adjustments to the children and use that children to repopulate the initial population. And you do this over and over until you have met some convergence criteria, or until you have simply run out of iterations. Is there any questions here? Because I'm talking all the way through, but I would like if you guys have any questions that I can answer also throughout. All right. If not, before I'm going to the next slide, I would like to mention that a last thing. You can, it does sound a bit restrictive to biology, but you can use this optimization techniques for a wide array of solutions. I mean, this technique is so good that it has been used by so many people in so many different concepts. So from like graph coloring to pattern recognition, where you can apply GA, from think about salesman model up until continuous systems, like designing an airfoil in aerospace engineering, to the financial market, to even motive engineering or optimization. So its applications are really, really vast.
Ismael, I don't think you can see the chat, but there are some questions there.
Oh, sorry. No, I didn't see it. Let me have a look. So I just bought a monitor for myself, so I'm not using two screens, but I'm still a bit amateur in that. Are there any Python packages, or is it all custom code? the problem with genetic algorithms, I mean, there are Python packages that you can use it. I don't have covered it in the slide, but think about Pygmo, which is a really good Python package. I will type it in the team where you can apply it. But there are, even if you have a package, there is still some custom coding that you have to do, and that all has to do with the crossover and mutation example that I'll explain over here. Sorry, I don't know what happened. 1 second, very sorry for this. Let me retry. Yes. All right, sorry for that. I pressed escape and I don't know what happened. The problem is when we go back to this slide here, you have to do some sort of crossover and mutation. That means that you have to transform your population factor in such a way that you can even perform a crossover and mutation. So you have to encode your solution vector in such a form where you can split them up and paste them in very different ways, or even do some point mutations to it. And that is something that you'd have to do it by yourself. You have to find a way of how to encode a population into a, like, for example, binary string format, like you see in this slide, to then apply the crossover and mutation to it. And once you have done that, you have to decode it back to the initial vector. And that is in genetic algorithms where the custom work comes into play. Before I'm going to get further into that, I would like to go through some questions. How critical is the start set of vectors? It is critical. I also cover some of these solutions actually in the slides later on, so I will wait with answering that question to keep the order of these slides, because I don't want to tell things now while the answer is like 2 slides away. So I hope you have a bit patience for that. Oh no, there it's not a curved monitor. Okay, getting back to a crossover and mutation now. So you have to see it like this. This is binary string which represents in some way your solution vector, and this is another binary string that also represents another solution vector. So this can be the 2 fittest solution vectors that you have selected, and you're going to apply crossover. So what you do is you split them in half, and you take the left part of the first string, combine it with the right part of the second solution, then you will get this. And you do the same other way around. You take for the other solution the left part, combine it with the first solution's right part, and you combine them around. So instead of having a parent solution like this and this, you cut them and paste them like this, which will become the crossover agent, and this one. So this is then the child gene pairs after crossover. So that is what you have to think of crossover. Like it's really just stitching and pasting large parts of pieces of the gene, and then going crazy with it. You have a lot of ways how you can do that crossover. I think there are about, on top of my head, 6 types of crossover techniques where you can have duplications, inversions, deletions, insertions, and translocations. So this is just a translocation. You change the location of this one and that one with each other. You can also just add a group of strings to it. You can even just remove a part of a binary string. So that there are many variants of doing the crossover. You can even do it at multiple points. And then you have mutation. A mutation is like, it's like a point mutation where you just change a very small area. So that is achieved by flopping a randomly selected bit, like this one. So you take this bit and you just randomly, you take a random bit like this one and you just swap it. You make this one a 0, and then you will get a new gene. So you have to work balanced with the crossover and mutation, but I'll get to that. In terms of time, okay, now the slide with the answers to many questions that you have had. What are the advantages and the disadvantages of genetic algorithms? If you look back at this slide, the way how you work with the population, the fitness selection and stuff, you can immediately already deduce like the most noticeable advantage being that it can deal with complex problems, but also the fact that you can parallelize it, because you can do so many things in parallel. So you have a parallel optimization technique. Genetic algorithms can deal with various types of optimization, whether the objective function is stationary or non-stationary, meaning whether the objective function can change with time. Because yeah, you can also have like optimization problem where the objective function is non-stationary and changes with time. So genetic algorithms can deal with that very good. You can also deal with objective functions that are either linearly or non-linearly. It can be continuous, it can be discontinuous, it can even have some noise to it. As multiple offsprings in a population act like independent agents, the population can explore the search space in many directions simultaneously. So which makes it really powerful for parallelization. Although there are also some disadvantages to it, and that is you have to encode or decode the parameters or your input vectors or the agents, you name it, into genes, such that you can apply crossover mutation and then decode them back to their original solution. Yeah, of course, your optimization problem also it will be sensitive to your fitness function, population size, rate of mutation crossover, and selection function. So the crossover problem, you have what you call a crossover probability. So you take the best performing genes, and depending on the crossover probability, you will apply a crossover to it, yeah, or not. Then you also have the mutation probability that depending on the probability that it gives you either perform a mutation or not, but it can be sensitive to that probability, because if a mutation probability is too high, what you will get is the diversity of the population may be too high, which makes it hard for the system to converge. And mutation at a single site is not very efficient. At multiple sites will increase the efficiency. So it's also about where are you going to apply that single mutations to, but you don't want to have too many mutations because it will make it difficult for the system to converge, or even for the system to go straight to the wrong solutions. And this, you can say the same can be said about the crossover probability. That will also change the way how your model will converge. And then you have also, population size. The right choice, the choice of the size is also important, because if the population is too small, the population size, there's not enough evolution going on, and there's a risk that the whole population may go extinct. In a small population, if a significantly more individual appears too early, what you will get is the offsprings will overwhelm the whole small population, and that will eventually drive the system to a local optimum. But yeah, you don't want that. You would want to go to a global optimum. So you don't want for good solutions to come a bit too early. So these are the things that you have to deal with when you build a genetic algorithm. So there are still some tweakings and doing so over here and there. So that's it on my part. I've been talking for quite some time, so thank you guys for your patience. I will now hand it over to, if you don't have any questions anymore, at least, I will hand it over to Susanne, who will go over the code with you. So we have prepared some example codes that shows how you can build a genetic algorithm for a certain problem. And now I can't stop presenting. I really have to take time to get my screen, to know my screen a bit better. So Suze, if you can share your screen, it will automatically stop sharing my screen.
Yeah, I'll do that. Thanks for the talk as well. Okay, well, thanks again, Ismail, for the theoretical introduction. And we'll now continue with a more practical introduction of a genetic algorithm. Probably all of you know the game Flappy Bird. And you probably all know that it's quite difficult to get a good score and get very far in that game. I can show you if you are not aware with the game. It's about a bird that needs to go through the wooden sticks, the wooden pipes, and when you hit the pipe, then you are dead, like this. Well, of course, this may not seem like a very important problem, but there is a nice way to resolve it with a genetic algorithm. And I'll show you how to do that. As Ismail mentioned, we have a few things that are very important in a genetic algorithm. That's the agent or a genome. That is evolving over time, and that will be optimized eventually. We also have a crossover function, and I'll explain this more in detail in a second. We'll have a crossover function and a mutation function for that, and we'll have a state. And of course, the most important thing is what we decide to do. So for Flappy Bird, you only need to press the space bar, and then it will go up one bit. So the important thing is to tick on the right time. So not too early, because then you'll bump into the pipe, and not too late, because then you'll bump into the lower pipe. And we'll start with what we need to do. So a decide function, if we need to press the tick function or not. So we want to optimize that. And we have written one that says if a certain value is over 0, then we'll do a tick, and otherwise we don't. And that decision is based on a certain state that we're in now. And that state depends on a few different things. So it depends on the speed of the bird. So how fast the bird is going. It depends on how many ticks you've done, and the distance between your bird and the next pipe. So the horizontal distance, and distance from the top of your bird until the most lower point of the pipe, and the top of the bottom pipe, and the lowest point of your bird. And we so those are 5 values that we have, and we have we start with an initialize of 1, and we initial value of 1, and we multiply those values with the genome. So the genome is the one we're updating every time, we're evolving that, and we're trying to get as good as possible we want to see as good as possible that if we decide to do a tick, that it won't hit to the pipe. And to do that, we multiply those values that I just mentioned with the distance between all the pipes and the speed of the bird with the genome. And the genome, that is, we first randomly initiate the genome, and then we're going to evolve that genome. And we'll do that using crossover and mutation. And let me go to the main script, because these are all the functions we use. So the different functions, and this is our main function, which we start with. These are to initiate the game and to set all the displays and a number of frames that we're creating, so the pages of the game itself. And we have a loop, so it will go on until until we stop it. And we'll try, this is just to handle that if you want to quit the game, you can press the key down or an escape button. But otherwise, we'll check and see if a bird is alive. Then we'll go on with this. So we'll generate a random pipe, and so that will be the next pipe to say. And we have just initialized all the frames by creating the frames, and that's just the world it's in. So that was the screen. If you want to see it, that's so. This is one world, one frame, and we create the frames with the width and height that we set itself, and with we start with 25 times. Here we initialize the value. We start with 25 times 25 plus 25 birds that start in the process. So we initialize that many worlds at the same time, so that we can create the program. And after we've created those frames and initialized, we'll go through every of those frames, and we check if the current frame did not die, then we'll have a look at the first value, and that's so in the create frames function, we'll have an initiated pipe with the width, height, count of that. The first one is randomly initiated, but we'll have it the same for every world, because we want to optimize, we want to check it for the same world, so that all the 25 times 25 plus 25 worlds are the same. And we'll do that by creating an individual. So we set a new genome, and we only do that for the first time, because otherwise we'll just use the generation itself. But now we create one, and then we'll make sure that we have an equi-world frame function, which makes sure that we'll have the same world for every genome. And if we do that, so we have the current frame. That's the frame we're in now. And if there's not one alive, then we set this to true, and then we'll paint the pipe, and then it will if no one is alive, or if not one is alive, then it finishes. But if there is one alive, then we are going to go through the decide function. So we're going to decide if we're going to do a tick or not. And of course we have the coordinates of the bird. So we're going to use that in the decide function, where we have the state and the current frame, of course, that's so with the distances. And for that we look at the genome and the state. So we look where a bird is now and what its velocity is, and we multiply that with its genome. And then we decide if we do the tick or not. And if we decide to do the tick, then we'll do it. And otherwise, then we'll add 1 to the impulses. So that's the number of ticks we have done. And we'll do a tick. So a tick is just to add a bit of height to the bird. And then we'll this is a function, or this is used to show the current frame with the bird a bit to the further in the game. And then we will set a next pipe. So we'll do that to create a new pipe in the game. And then it checks if the current frame, if the bird collides with the pipes. So if the bird has collided with the pipe, then we'll say, well, on this tick, so we count the number of ticks, and on this tick the bird died. So that's the fitness of the bird. So if he dies in after 20 ticks, then the fitness of the bird is 20. And we'll continue that for all the frames. So we have those, we have all the worlds we've created. And after that is done, we'll show all of the, we'll display all of the new states of the birds in the frames. And if they all died, which they eventually do, then we'll start the evolve phase. So then we're going to create a new next generation, where we're going to evolve the genomes. And the evolve function, I can show you. The evolve function is where we, so they all have a number of ticks, and that's the died function. And that's part of their, we have a total population, and they all have a number for the number of ticks they survived. So we sort them first by the number of times they survived, and then we take the elite of that, And we take the elite by ordering them from 0 to reordering them, and we take the fittest 25 in this case, because our top is 25, and we take a random sample of the last of the others from the size also 25.
So
and
this is just Suzanne. So this is the fitness. The fitness is determined by how many ticks has each of the birds survived. So that's why we take an ordered list of all the individuals, reverse sorted by I dot died, which is the number of ticks that it survived. So we take the elite, then exists contains the best performing birds plus a random selection of the worst performing birds. Sorry, Suzanne, go on.
Yeah, no problem, thanks. So we indeed take, we then end up with an elite, and with that we print those elites to show them, and then we're going to do to use the crossover and mutation function, and we do that for every combination for A and B, and all where we have so we where we apply crossover and a mutation. And the crossover and mutation function I'll show you. So here we have set the mutation chance at 0.01, and that means that with a chance of 0.01 we apply this, or it will apply mutation. And in this case, it will create a child genome, and then it will mutate that with a chance of 0.01, and it will mutate that by with a random number between minus 0.5 and 0.5. So it will or add or remove, or it will add or subtract a 0.5 from a number, and then it will keep that as the next genome. And we can also do crossover, which we have the same individual, and we'll have a cutoff point there, and the cutoff point is a random number between, or that's a random number between the length of the genome and 0. So we'll take we take the genome, one genome, and that will from its cutoff point itself, it will take the other genome. So for example, if you have a genome, if the cutoff point is 2, then the first 2 numbers will be from the genome itself, and the rest of the numbers will get generated from the other genome, and that will be the child, and I will continue with that one. And to go back to this function, so the evolve function, so it will do that for the complete elite, and it will do that for so it will combine all the it will do that for the complete elite, and it will do that also in combination with every A and B that is greater than A. So it will end up with all the combinations between A and B, all the unique combinations. And let me see. So after that, it will, then we have our next generation. We have the next generation of evolved people. or genomes, and after that we will create the new frames with the same width and height we've just had, but then we don't get a random initiation, but we'll do the but we'll use the generation we have created now, and that will be our new frames. We'll set the tick again to 0, and then we'll add 1 to the generation, and then the whole thing starts again. Let me see. Are there so far any questions, maybe? Okay. Well, I can show you at least how this works. So let me first show you this, then you can see. So it now tries to start the game. It starts the game, and these are all the frames that you're seeing, and you see that a lot of them are deleted because they're bumping into the top of the or the bottom from the screen. And the further we go, the better the program gets. So you see that here a lot of them bump to the pipes, and now every time we get more and more birds through the pipes, and then after a while we have one that can get through a lot of them. And you see already that it's evolving quite fast, quite good. As you can see, we have, I think, still 2 birds left that are getting through. And if we'll, so at first it goes very fast, and then it slows down with how far they get. So it takes a long time to train them in such a way that they can go through the program itself completely. But you can see that a lot less of them bump into to the bottom yet and to the upper one, and you see here that we still have a few of them left, and every time it gets more and more that we'll see them. And to show you, this is the these are the fitness. So let me see. So we'll print, where do we print that? Well, we're printing the fitness. So this is our genome, this last bit. So this is what we end up with. So the initiated values between -5 and 5. And this is what we end up with. And this is the number of ticks it has survived. So a few of them have quite a lot of ticks, and you can see that the first 25 we have picked. So here we print them. So the first 25 have survived this long, and then we picked a random sample of the others. So that's this one, and you see that those scores are a lot lower than they used to. And you see that here the most number of ticks was 565. And you see while we'll go through, here now it's already over 6,000 ticks. So you see that it's evolving quite well and quite good. And you also see that a lot of the birds died at 5,109 ticks apparently. But you can see that, they're evolving quite fast, quite well into the program. And as you can see here, now we have, it's still running on the background, but now we have quite a few birds that are still in the game, and they're they're becoming quite good at it. So as you can see, it increases every time we run it. Okay. Are there at this moment any questions? Okay. Yeah, so what the main things of the genetic algorithm are the cross-validation, the mutation, and of course setting the genome. And I know that someone asked if it's important what the initial value is. Well, you see that we randomly initiated the first time, and that's the idea, so that you have so that you are on quite some spaces in the input space, and that you then can start. But yeah, we initiated randomly, so it doesn't matter where you start. And yeah, if you change the value of 0.1, it will mutate more often, so you will get more values. But if you increase it, then the probability, then you get to more spaces in your input space, but the probability that it, if you set it too high, then you will be all over the place because you keep evolving. So you can change, or you can play a bit with this. Yeah, I think if there are... That's messed up. Yeah, so you can see that it works quite well for, and this is a simple problem, of course, but you can always also use it for optimizing a machine learning model, or picking the right features. Yeah, so yeah, are there any questions left yet?
One question.
Yeah.
Because you use the number of ticks as an indicator for success, is then the bird biased to go through the top of the opening instead of in the middle?
So the number of ticks is just how long has it survived?
It's not the number of times the spacebar has been pushed.
No, this is
okay.
the time tick. Yeah.
Okay.
We could change the fitness function to be to also take into account the number of spacebar hits, like the number of ticks divided by the number of spacebar hits, for instance. So if you were survived many spacebars, then yeah, you're penalized for how often you hit that. Does that answer your question, Mike? I think it was Mike, right?
Yes. Yes.
Yeah. Okay.
Oh, cool. Any other questions or suggestions?
if there's no more questions, then I think we can conclude this pizza session.
Yeah.
Yeah, thanks a lot, everyone, for attending this one. Of course, we will share the code. Paul will send around a link to the GitHub repository where we maintain all the code of the pizza sessions. Stay tuned. Thank you very much for joining today. I hope you found it interesting enough to keep an eye out on the other pizza sessions that we're organizing. There will be one in January. I think the date has already been set. Suzanne?
Yeah, the 29th of January, out of my head. The last Friday in January, at least.
The last Friday of January it will be. We decided to skip December because people are busy doing other stuff normally. So yeah, hope to see you back in the last Friday, or on the last Friday of January, where we have our own Paul May for a yet to be disclosed subject. So keep an eye out on that one. For now, I wish you all a great weekend. No pressure indeed. I wish you all a great weekend, and yeah, hope to see you next time.
Bye, everyone.
Okay.
Have a good weekend.
Willem.
Mike, ik ga even kijken of ik de recording uit kan zetten.
Oké.
Tot nog toe lukt dat niet.